know not how to kill me when I come in unconscious and I can't tell you how not to kill me. Okay? And so an oxidation reduction reaction is a reaction where electrons are transferred. A lot of times these are called redox reactions. Reduction, oxidation, redox. Redox is easier to say than oxre. Right? Oxred? I don't know. Redox is easy to say. So this is an example. If we take zinc metal and react it with copper ion that's in solution, we're going to get zinc ion and copper metal. So over here the zinc was metal and the copper was ion. Over here the zinc is the ion and the copper is our metal. In order to make that happen, electrons have to be transferred from the zinc to the copper. Look at the charges here. There's no charge written on that zinc. So what does that mean the charge is? 0. If no charge is written on something, it actually has a 0 charge. What is the charge on the zinc over here? 2 positive. That means we lost negatives. Electrons are our negatives. And so we lost electrons. Copper started as 2 positive and ended up at 0. On a number line, 0 is more negative than positive 2. Go from positive 2 to 0, right? You're going down. You gained negatives, so you gained electrons. This is what this looks like when you actually do it. And again, this is a reaction that you'll do in lab. And so what we have a beaker. In the beaker is a solution that had copper in it. It's probably copper chloride, copper nitrate, but the chloride or nitrate don't matter. It's a spectator ion. So once you dissolve it, you have your copper ion. We then put a piece of zinc into the solution. If you zoom in, we have our big chunk of zinc, and then we have our copper ions floating around in our solution here. If one of those copper ions hits that piece of zinc, they're going to be touching for a split instant. In that split instant, electrons are going to come out of the zinc into the copper. That copper is no longer an ion then. It becomes copper metal, a solid, which is not soluble in water. And so you get a layer of copper metal forming on the outside of your zinc strip. The zinc went from insoluble zinc metal to soluble aqueous zinc ion. And so the piece of zinc actually comes off and goes into the solution. So if we look at how blue the water is, over here it's very blue, over here it's not nearly as blue. The blue in the water comes from the copper ions. Copper ions are blue. We lost our copper ions because they went from being blue in solution to being copper metal on the outside of our strip. That's what happened in our oxidation reduction reaction. So it's an oxidation reduction reaction because there are 2 processes that happen here. Something gains electrons and something has to lose electrons. Those electrons get passed directly from one thing into another. They don't fly off into space and then come into something else. They go straight from one thing to another. And so we're going to have a list of definitions. And these are all definitions you need to know. The first one is oxidation. Oxidation is the process of losing electrons. It doesn't matter how many. If you are losing electrons, that is oxidation. Reduction is gaining electrons. You can memorize them. The way I remember them is what happens to the charge. So if we go back here, which one gained electrons? Copper gained electrons. What happened to its charge?
It was zero.
It went down, right? It went from a positive number to 0. The charge went down. The charge was reduced, right? If it was reduced, it went down. And so the thing that gains electrons is reduced. Its charge is going to go down. Oxidation must be the other one. Oxidation has nothing to do with the number going up. So I remember reduction is the one whose charge goes down, so the other one is oxidation. Yes?
Is that like a dialysis tube in the picture? One of those.
This?
You sink in.
No, this is just a piece of zinc.
Oh, okay.
It's hard to see. It's a little better. It's just a silver strip of metal. That's all it is. So if you have oxidation and reduction, they always happen together. Because I said electrons get transferred directly to one thing, from one thing to another. And so as one thing is losing them, another thing is gaining them. Oxidation is the process. If you lose electrons, we say that you are oxidized. You underwent oxidation. You were oxidized. If you gain electrons, you underwent reduction. You were reduced. So the thing that loses electrons was oxidized. The thing that gains electrons was reduced. That, if that's where it stopped, is pretty straightforward, right? As long as you can remember that, that is fairly straightforward. The next two things are backwards, okay? Don't blame me. It does make sense when you really break it down, but at first sight, it seems backwards. So the element whose charge goes down, we said was the thing that was reduced. But we call it the oxidizing agent. The thing that was oxidized is the reducing agent. Agents do something to something else. So if you were reduced, you oxidized something else. If you were oxidized, you reduced something else. And so my suggestion is assign which one was reduced and oxidized, and then just remember that the agent is the opposite word. If you were reduced, you were the oxidizing agent. If you were oxidized, you are the reducing agent. So like I said, when you break down the actual English words there, it does make sense. But it's confusing because reduced is the oxidizing agent. It flips. And there's really no good reason to do that. They could have come up with better words. Yes?
So like, examples like iron, it's a reducing agent to salt. Because I know when many metals are exposed to salty air, they rust faster.
Like that.
Yeah.
We'll get to it in a few slides. You're thinking. Good for you.
No, I'm just asking if that's how you.
Yeah. We'll work it out whether iron is the oxidizing agent or reduction agent. So in order to do this, in order to assign which one is oxidized and reduced, we assign what we call oxidation numbers. And for the most part, at least in this class, oxidation numbers are the charges. Okay? We're not going to make it more complicated than that. It does get much more complicated than that. Okay? So in this case, what we've done is we have assigned oxidation numbers. Normally you'll write the oxidation numbers above each element. So the oxidation number here, we said for zinc, was 0. There was no charge. We said the charge was 0. and so it's 0. When copper is an ion, it has a 2 positive charge. Chloride ion has a 1 negative charge. This deals with the element, not the fact that there are 2 chlorides. Each chloride has a negative 1 charge, so the oxidation number is 1 negative. And so if you look at them, the zinc number on zinc went up. The number on copper went down. And so that is what I look for. I assign my numbers. I look for the one whose number went down. Copper went down. So copper was reduced. If copper was reduced, it is the oxidizing agent. If copper was reduced, that means zinc must have been oxidized. Process of elimination. If zinc was oxidized, zinc was the reducing agent. Chloride didn't change, right? So it was neither. It was a spectator ion. It was not a part of this reaction. So this is a table of rules on how to assign oxidation numbers. So I blocked out 3, 4, and 5, and at least 6, possibly number 7. There are a bunch of rules for assigning oxidation number, but most of them make it more complicated than we need to make it. So I've only left the ones that are important to you, and they're exactly what we've already talked about. So number 1 says oxidation number of atoms of an uncombined element is 0. That means if you have an element by itself, the oxidation number is 0. But that's exactly what we did. Zinc, we said, has a charge of 0, right? Because you're never going to see an element by itself with a charge. You're just not going to see that. It's 0. If you see an element by itself, not an ion. If it's an ion, that's a whole different story. An element by itself has an oxidation number of 0. If we come down to number 5, we'll come back to 2. Number 5, it says group 1 elements have an oxidation number of positive 1. What did we say the charge is of a group 1 element? Positive 1. Group 2, we said with positive 2. Group 2 has an oxidation number of 2 positive. Group 17, which is the halogens, we said had a negative 1 charge. They have an oxidation number of 1 negative. And so what this group 5, what number 5 says is whatever the charge is, that's the oxidation number. And then number 2 says the oxidation number of all the atoms in a substance, meaning in your compound, has to equal the total charge for that compound or for that molecule. And so I can't think of an example where you're going to have a molecule, a complete molecule, that has a charge on it, right? If we have sodium chloride, the positives and the negatives cancel out. Calcium sulfate, the positives and negatives cancel out. As a whole, there is no charge. So if you do the charges correct, number 2 works itself out. Because if you have calcium, let's do calcium chloride. Calcium chloride. What is the oxidation number on calcium? 2 positive. What's the oxidation number of chlorine? 1 negative. But I have 2 of them, and so I have a total of negative 2, positive 2, which is 0. And so my total oxidation number for the whole thing is 0, and my charge on the whole thing was 0. And so you don't really have to worry about that. But if you see that these don't work out, that's telling me you assigned one of these incorrectly. Where number 2 really comes into play is in a more complicated situation where you have a polyatomic ion. Let's say we had calcium sulfate. You can't assign oxidation numbers to a polyatomic ion. You have to assign them separately. And so this is more complicated than you have to do. And so you would assign calcium, because calcium is always 2 plus. One of the rules that I blocked out says that oxygen always has to be 2 negative. And so then you make sulfur whatever it has to be to get the whole thing to 0. But you don't have to do that. When you're doing things like this, you're going to have easy, simple ionic compounds with monatomic ions. Where you just say calcium is +2, chlorine is -1. If I do my subscripts correct in my formula, my oxidation numbers are going to come up to 0 automatically. So element by itself is 0. In a compound, figure out what charge that ion had, and that's the oxidation number. Get those written out and then see which one went down, that one was reduced, and then you can assign all the other names based off that one flag in the sand, right? Which one is reduced, all the other definitions can be figured out based on that one. So what's the oxidation number of that?
2.
No. 0. It's magnesium on its own, so it's 0. What's the oxidation number for? Actually, we're going to use rule number 2. We got calcium chloride. That's not calcium chloride. It's copper tetrachloride. Carbon tetrachloride. We're almost done. Carbon tetrachloride. And so nothing in here tells us what the oxidation number for carbon is. But we do know the oxidation number for chlorine. What is the oxidation number on chlorine? 1 minus. So how many minuses total do we have? 4. And so for the whole thing to come out as 0, what does carbon have to be? 4 positive. Yeah. Just like the charge, yes. Because carbon, we said carbon doesn't like to form charges. We don't see those in ionic compounds. We said it's in the middle. It can go either way. It can go 4 positive or 4 negative, and it's going to get to a noble gas. It doesn't like to form ions. And so in a compound like this, where you're assigning them, carbon can actually go to 4 negative. But in this case, it had to be 4 positive. What's the oxidation number on the sodium then? +1. And the chlorine is -1. It's in a compound, and so assign the charges, and those are your oxidation numbers. Now we'll talk about the rust. Rust, the process of rusting is an oxidation reduction reaction. And so we've got a zoomed in picture here. And so what we have, this is iron here, and then there's a water droplet sitting on our iron. This is a spot that's already rusted. And so if you oxidize iron, do you know what rust is? It's iron oxide. Okay? So we're going to take iron and oxygen that is in the water. It's oxygen gas that is dissolved in the water, and electrons are going to be transferred between the two. And so here, this shows an ion going from the iron. Yeah. And so the iron here is showing iron makes iron ion and gives off electrons. And then it shows oxygen, water, and those electrons come together to make hydroxide. So this redox reaction is more complicated than what we did. This is more complicated than what you will have to do on an exam or quiz. But this is probably the most relevant redox reaction to life, right? Everything rusts. Our blood is red because of this, right? It's basically rust. And so what happens is the oxygen comes out. Once it gets the electron, it's going to then react with our iron to make iron oxide. And also, some of our iron turns into iron ion, which dissolves in water. So if it's raining, and this is happening, and then the iron dissolves in the water, and then it drips off. So that's why you get a hole in something that rusts. Because a lot of your iron dissolves in the water and then disappears. What's left behind, that powdery red stuff, is the iron oxide. Because you end up making both. You make iron oxide and you make these floating iron ions. So we can prevent this from happening a number of ways. What's the easiest thing you can do to prevent something from rusting?
Wax.
You can wax it,
Clean it.
clean it,
Just keep it
Rinse it with water.
keep it dry. What if you have a car?
Oh, don't leave it under a dripping tree all the time.
That's going to keep the water off. If you have a car and you get a ding on it, it's going to rust, right? Why is it going to rust where you dinged it? There's no paint. The paint and the wax create a barrier. The water can't touch the iron and the steel. And if they can't touch, they can't react. We need to transfer those electrons. And so the easiest thing you can do is just keep them from touching. So if you have copper or brass, the same thing happens, but instead of making rust, you're going to make a green corrosion. Pennies, you've seen they get dull, right? That's one form. You've probably also seen really old pennies. They're all dirty. They get green stuff on them, right? That is also corrosion. If you've seen brass sculptures or brass anything, if you have brass fixtures in your house, if you don't keep them clean and polished, they get green on them. That's corrosion. If you have silver jewelry, they get tarnished, right? Silver tarnishes pretty easily. You constantly have to either polish them or you keep them in a pouch that keeps them from tarnishing. The silver reacts with the oxygen in the air to make silver oxide. And silver oxide isn't shiny. And so you get that very thin coating of silver oxide, you just take that off and you expose the shiny silver underneath. We can also prevent things from rusting in a more chemistry-related way. Because painting everything doesn't always make sense. If you have something completely massive, painting it doesn't make sense. If you have something that's continuously going to get bumped and you keep scraping off the paint, that doesn't make sense. Anybody here who has an outboard motor? On your outboard motor, have you ever seen the little silver plates? You know what they are?
No.
They're called sacrificial anodes. And so on this outboard here, usually you see them right above the propeller here, and you'll see them also where it attaches to the transom here. That's zinc. A lot of times there are also some of the nuts that hold the propeller on will also be made out of zinc. Zinc corrodes easier than iron. And so what happens is you put your motor in the water, the oxygen in the water is going to steal electrons from the iron in the steel. But then the iron just turns around and steals electrons from the zinc. And so your outboard here is made out of steel. If the water steals electrons from that, this steals electrons from that. And so your steel, in the end, does not lose electrons. And so it doesn't rust, it doesn't corrode. The zinc, though, does. A brand new outboard has these shiny, nice little zinc things. They're smooth, they're nice. An older one, what you probably have, is kind of white colored, it's dull, and it has these little lumps all over it.
Yeah.
That's zinc oxide. Because your motor essentially rusted for a split second, but then it unrusted when it stole electrons from that zinc. It's called sacrificial because when this gets used up, you just take it off, you put a new one on. It's a lot cheaper and easier to keep replacing these than to replace your outboard in your whole motor constantly. Giant ships have these gigantic ones on their hull. They're usually below water. Some of them can be up above, though. That keeps the ship from rusting. Occasionally, they have to go through and pull all of these off. Was anybody in the Navy? Coast Guard, anything like that? Okay. But giant ships have these because their hulls will rust. Most boats that we own, they're either aluminum, which doesn't rust, or they're fiberglass, which is basically plastic, which doesn't rust. But a giant ship can't be made out of aluminum or fiberglass. Fiberglass is too expensive, aluminum is also too expensive. So they have to make it out of steel. But steel rusts, and so they put these zinc pieces on there to keep it from rusting. They do the same thing for oil pipelines. It'd be too expensive to use aluminum for all of those pipes, and so they go through and they put these sacrificial anodes along the piping. That prevents them from having to paint it, which would be a lot of paint. Prevents them from having to go back through continuously and repaint them every time a grizzly bear bites one of them. Mm-hmm. And so all they have to do is every few years pay someone minimum wage to go through and replace all these zinc anodes. Electroplating is essentially the opposite of corrosion. Yes, that is a gold-plated DeLorean. If you electroplate something, you essentially undo oxidation. And so with the iron, we said when it oxidizes, the iron turns from iron metal into iron and it disappears. If you're gold plating something, you start with gold ion, you pass electricity through it. When you pass electricity through it, you take gold ion. If we have a gold ion with a 2 positive charge, we add electrons to it, we get gold metal. We take a charge from 2 positive to 0. But gold metal is not soluble in water. And so it's going to stick to whatever is conducting that electricity. So if you have a piece of jewelry, you hook one electrode up to the jewelry, then you take the other electrode to stick it in the water that has the gold ions in it. Electricity will go through them, you'll make the gold metal, and then the gold metal will form a coating on the outside of your jewelry. I would imagine for a DeLorean, you probably have to do each part separately. Because if you take the DeLorean and you put it underwater, it's probably now a gigantic paperweight, right? And what's the point of having a gold DeLorean if you can't drive it? And so I'm guessing you have to do piece by piece. So that is redox reactions. That is what you need to be able to do. You need to be able to tell me which thing is reduced, oxidized, which one is the reducing agent, which one is the oxidizing agent. Everything on this lecture is fair game for the quiz next week. Okay? We'll talk about the exam next week on Tuesday.
So are we turning in other labs, or because you said in the email there was the makeup lab?
Yeah, so the makeup lab is just if you miss a lab, you can do that one.
Okay.
So if you don't miss a lab, you don't.
Okay.
It's just what is that came in kind of late?
That's not like
I was able to do like organic and inorganic. Like, or do you think like I shouldn't even try?
I have no reason to
I
know that.
go for like medical science, do all that.
That's all. It's where organic is on the MCAT. Inorganic's not on the MCAT.
That's not?
Where